are going to talk about tunnel diodes here. Okay, we're going to talk about tunnel diodes here, and but then before that, what exactly are tunnel devices? So tunneling is basically a quantum mechanical process, right? That is something which you all know. Okay, so based on this, we can actually write down some important points that we should actually know about. Okay, so this is basically a quantum effect, so it will have some advantage, right? So advantages of this quantum effect device. Okay, quantum effect device. So what are the advantages? Okay, so let's just list down few. Okay, let's just write down the first one is works at room temperature. So think about it in this way. In general, when we actually want to have some kind of current from a device, from an electronic device, maybe a semiconductor or a metal, we need to apply some kind of voltage. Okay, for semiconductor, we need to apply at some point also some temperature. But if we have this tunneling effect, then the electrons can be available for the conduction process even at room temperature also. Okay, because this is a quantum mechanical phenomena, does not really depend on the temperature every time. Okay, it does have again a high switching speed. So just like we have seen for Schottky diode that it has got a high switching speed. Okay, similarly any tunnel device will also have a very good switching speed. So we can basically use it for a on-off system. Okay, and of course low power consumption. Now low power consumption, I think it's quite obvious, because whenever you have any kind of device and you want to get current out of it, you need to apply some voltage. So if you already have an additional, so initially we do have the thermoionic electrons. Okay, yeah. But if we have a process like tunneling, that means in addition to that thermoionic current, we are also getting the tunneling current. So that tunneling current is also obtained using the same voltage. Okay, so we have got an additional charge carrier there. So as a result of which, desirable amount of current we can get it. Okay, even by not using too much of voltage. So that means it has this advantage of low power consumption. Okay, and if we just look into the working principle, okay, or working mechanism in general, okay, or operating principle, working principle, whatever you want to say. So in general, if I just write down the working principle, probably, I'll just write down a few points. One is the quantum effect, right? So we basically have the quantization of charges. So quantization of charge is very important. You already know about it, right? So you cannot have charges which will be actually continuous in nature. They are obtained in quanta or quantities. Okay, so that's quantization. And then we have got the process of quantum tunneling. So quantum mechanics. If you want to understand a lot of physics and you want to know the reality about any kind of phenomenon which is more or less uh, nature, okay, we have to so we have got the quantum tunneling. Okay, and then there is something else which is called negative differential resistance. Okay, negative differential resistance. So what does it mean? The term negative is important here. Okay, it simply means that in general, what happens is whenever you are actually increasing the voltage, the current will increase. Okay, but in tunneling devices, okay, what happens? Increase in voltage. Okay, maybe I can write this. So voltage and current will actually reduce. Current will reduce. Okay, and that is basically called a negative differential resistance. Okay, so if we have the increasing voltage here, okay, the current will actually reduce. So these devices are such. Okay, so depends on how they are designed, and depending on the tunneling effect, we can actually decide that. Okay, but one more thing that you might have already come across is this particular figure, and this is something which you already know because you might have studied this in quantum mechanics even in your undergraduation days. Okay, so if I just try to just figure these points out. Okay, see, this is your region A. So maybe the electrons are at this particular region. Okay, and then there is a potential barrier which it has to cross so that it becomes free electron. So in region B, we can actually say that this is the free electron. Okay, but then in region A, it is bound electrons. So if to cross this potential barrier y to x. Okay, but then in tunneling effect, the height is less important, the width is more important. So how much width it has to cross, depending on that, you'll be getting your tunneling current. Okay, so the basic logic is simple, which we already know. Okay, and so if, or in order to have this phenomenon to work actually, okay, what we need is we require it's not that you will have tunneling effect for any kind of electronic device. It's important that we have a fixed barrier height. Okay, so we finite barrier height and a thin barrier width. Okay, thin barrier width. So the width plays a very important role. If the barrier width is too thick, then the chances are that you won't be getting any tunneling current. Okay, and what exactly we do with the calculations here? How do we know how much probable is to have a tunneling current in a particular system? Will actually depend on your quantum mechanical calculation. Okay, so you would need a quantum mechanical calculation. Okay, and then if you just recall quantum mechanics a bit more, okay, you know that you have to consider this concept of wave particle duality. So I suggest all of you to please go through these topics you already know about. Okay, and then if you want to find out what is the tunneling probability, where there really would be the probability for the electron to come out of the system and contribute to the conduction process, we actually can find it out with the help of Schrodinger equation you can use, and we can actually do it. Okay, so this has got a very straightforward idea. Okay, and if we have a complex barrier shape, see, it depends on what kind of device you are doing it. Okay, here I've got a straightforward straight barrier with W. Okay, but then if you look into the picture that we have seen in our, we know that even if if we consider something like a Schottky diode, the barrier is something like this. Okay, and this is the width. So it has got different width at different regions. So the chances are that you will have more tunneling in the region where the width is less. Okay, so this is not very complex. But then if we have a very complex barrier width, you basically use a WKB approximation, if you remember. Okay, so you have to just go through that. But then anyway, I'm not going to ask this question in electronics. But then this idea should be clear that if it is a complex barrier, we basically use the WKB approximation. We are going to talk more about, you are definitely going to learn more about quantum mechanics. Okay, you have studied already a lot of it. Okay, but then there are more things that you should know. So advanced quantum mechanics will actually deal with this. Okay, so this is what is this all about. Okay, and any kind of tunnel device. So I'm just talking about tunnel devices here. So any tunnel device, it might be a tunneling diode, okay, or it might be any other device which basically works on the phenomenon of quantum mechanical tunneling. Okay, all of these tunnel devices will basically work on this. And if you want to analyze a device which actually works on this tunnel effect, you have to talk about WKB approximation, Schrodinger equation, and so on. Okay, so how do you exactly design this tunneling devices? Okay, so there are certain fabrication techniques. Okay, so as we are already studying about characterization technique. Similarly, you can also study about fabrication technique, how to fabricate. So let's say I have got a semiconductor and I want to fabricate a junction diode. What is the fabrication method about? It is all a separate topic altogether. Okay, we just started the physics here, but then fabrication topic is a subject in itself. Okay, so we in general, for any tunneling device to work, we actually need heavily doped system. Okay, heavily doped semiconductor. Okay, so it should be heavily doped. Okay, and the junctions should be more or less abrupt. So that means if you have a metal semiconductor junction, it is basically an abrupt junction. You don't have a smooth transition there. There is a discontinuity that is working, and that discontinuity actually adds to this width of the potential barrier, and that junction can be considered to be a abrupt junction. Okay, so we can fabricate using different methods. Using methods like this is not an exhaustive list, but then we can actually fabricate such devices. Okay, and then we can actually do something like ion implantation. So I think ion implantation, the name explains itself, that we actually have the ions which are working, and then basically they will be included into the system. Okay, so if you want to actually have a metal doping with the semiconductor, you want to make a junction there, you can actually use the ions to implant it. Okay, and then we can actually have another technique which is called rapid thermal diffusion. Okay, so diffusion, that is important. Okay, and then something which is actually not financially very promising. Okay, you actually need to have a lot of financial support for this molecular beam epitaxy. So there are institutes throughout India where actually these setups are there. These are actually assembled systems. You cannot really have a company selling a molecular beam epitaxy system. Okay, it will more or less look like a machine which might be looking like a transformer kind of movie. Okay, where you have those machine kind of structures. Okay, but then those are actually used to synthesize the sample, and those actually are costly. Okay, you need some finances to actually use them. And then we also have got the laser diffusion. Okay, laser diffusion. So you have the energy of lasers being used to actually diffuse and make the samples. Okay, for tunnel devices. Okay, so if you are making a tunnel diode, we'll also use a similar technique. Okay, so this is what is important here. So having said that, I think we should actually talk about the tunnel diode now. Okay, so let's just write down few specific points about tunnel diode. Okay, so tunnel diode is actually also has the name after the process of actually making electronic goods circuits. Okay, so that is also called as Isaki diode. So that's our top. Then if you know the tunnel effect, I think the working of tunnel diode is something which is very obvious. Okay, so what we can do now is we can just write down a few points here. Okay, so this was introduced. It's not that it was discovered because this effect was known, okay, for a long time. Okay, but then during that time it was actually new. But then since this effect was known because quantum mechanics came into the picture and something like tunneling was probable and understood at that time. Okay, so it was actually introduced by Leo Isaki in 1958. Okay, and another important point might be how they are doping it. Okay, we already know it. It is heavily doped. So in general, when we actually study about diodes, we say, okay, it's a simple device. We have a P junction and we have an N junction. We simply use them actually as a semiconductor device to make electronic circuits. But then it's not as simple as it looks. It depends on what is your utility. If you want to use it in reverse bias, you use Zener diode. Use it in forward bias, you use LED, so on, right? So we already know that there are different applications based on how a simple semiconductor is doped and so on. Okay. So as I've been always talking about, what exactly do we mean by heavy doping? Okay. So in a heavy doping, what we say is that the impurity concentration. Okay. So if we say that, what do you mean exactly mean by heavy? Does it mean that I do a 50-50 doping? The answer is no. If you say a word like doping, doesn't mean that you dope it like 50-50. Okay, that's not doping. You are actually making an entire new compound. Okay, you are mixing two compounds. Doping means you are adding the impurity in small amount. Okay, so the doping concentration is actually 1 part. Okay, in 10. Okay, how to write that exponent to get it? I will use this. Okay, so it's 10 to the power 3. Okay, so to every 10 to the power 1000 atom, okay, we actually have the 1 atom that is being added, impurity. So if we are actually doping, let's say, germanium and arsenic, right? And you have, that is a semiconductor, but then I'm doping, let's say, silicon, I'm doping it with another compound, a group 3 element, and then I will just take 1 atom of that group 3 element to 1000 atom of silicon. How do I measure 1000 atom? No, the answer is no. You have some amount, and then you can use your Avogadro's number and all, and you can know how many atoms are there, and based on that, you calculate how many atoms are actually needed for doping. So this is your heavy impurity. Okay, but if you consider a normal p-n junction, okay, how is the comparison? It is actually nothing but 1 part in 10 exponent 8. So 10 to the power 8 atoms, we are actually using 1 part. Okay, that is actually a normal p-n junction. But we talk about a tunnel diode, the doping is different. 1 part in 10 to the power 3. So please remember this. Okay, I think some figures are very important. And what about the width of the depletion layer? It should be thin because it has to undergo tunneling effect. So if it is too thick, you can expect that it will actually undergo tunneling effect. Okay, the width is small. Okay, and it's approximately, you can actually, they do some kind of band energy tuning and all, or sorry, the depletion layer tuning, okay, layer tuning. So this is the, okay, so with this with this one, okay, with the what, I think I should write it down, depletion angstrom, okay, so that's important. And I think this is something which you already discussed, but let's just repeat it. So in general, if you have a Schottky diode, then also we can use this, but since we're talking about the tunneling effect, okay, we actually can have a semiconductor system. We don't need a metal semiconductor system to looking into a tunnel diode, okay. So it might be a semiconductor system also, okay. So generally it is made up of germanium and gallium arsenide, okay. So gallium arsenide is a semiconductor, germanium is a semiconductor. You can use them, it will actually show this, okay. So this actually shows a tunneling phenomena. So maybe I can tunneling phenomena method process, okay. Let me write it down, phenomena only, okay. And I think that's the important point about tunnel diode, okay. If someone asks you separately, how does the physics work, we have already studied in our fourth and the fifth lecture, okay. And what else did I miss? I think I should write down the symbol here, so you already know it, right? So it's a tunnel diode. So it's simple, if you remember. Please don't mix up the symbols, okay. I think this is important. Zener diode is the other way, this is directly at this direction, okay. So always need to use the symbols, that's very important, okay. And then I think I can just write down anode and cathode here. Let me just try to be as complete as possible. Anode and cathode. Okay, so if someone asks you to write down a short note on tunnel diode, I think this should work, okay. And then we can actually talk about the diagram, okay. And then if more marks are given, then you can actually include the physics behind how does the tunnel diode work, okay. So what is the, so if we just write down a small note, okay, note, maybe I can, you know, it's all about the tunneling effect that you know, okay. But then I think this is important. So classically, we can basically talk about classical mechanics, okay? Classically, carrier. So you know, if I have electrons, the electrons will be the carrier, okay? So the carrier, I think it's too big. Just carrier must have energy, okay? At least equal to potential height. At least you know, if I've written in the previous diagram is ux, the energy must be comparable to that. But in tunneling effect, okay, in quantum mechanically, it might not have that, okay. There is a probability to penetrate. Probability to the width. Okay. Even if the energy is less than the barrier height. I think this is fundamental difference between classical mechanics and quantum mechanics. Okay, so this is something that's important. So let's just concentrate on this term barrier height. Okay, that is important. If you don't know the barrier height, it becomes a difficult task. So you know. Why tunneling is such an important phenomenon, because as I told at the beginning that if you have the energy, okay, and then you have the electron in its own favor, so that it can actually contribute to the current even without giving enough voltage. You give the voltage so that the electron can overcome the barrier, right? So if we actually have a process where it can overcome the barrier, I have to give that sufficient energy to it, okay. But then here we are not doing it, okay. What we are doing there is basically relying on the tunneling effect, okay. So maybe I can just write down This another important note here. Tunneling effect. I can write down effect. Lesser consumption of power by the chips. So you have an electronic circuit which is actually made out of chips. Okay, maybe I can write down electronic circuit. Okay, so I think this is important. Just take it on top. Okay, so this is another important point that we should actually look into it. Okay, and then there are oscillators and bistable circuits. Okay, differentiator comparators, those kind of devices. Okay, where we actually can use these tunnel diodes, which plays a very important role. Okay, so this is what I'd like to tell you about tunnel diodes, and I think this is important because this is very simple, but then the idea is important here. Okay, so some important properties, maybe what we can write down is maybe another page. Properties of tunnel diode, maybe already know some property, but then I'll just list down some more. Okay, so let me write it general. So what are the additional properties? The first thing, it is got a negative resistance. Okay, the first one is it has got a negative resistance. Okay, so in negative resistance, what really happens is, I think you already know it. Okay, if you look into the IV characteristics, okay, of in general, what happens is if you have the voltage here, okay, and the current on this side, expected is that as current voltage increases, the current will increase. Okay, then this device works in this particular junction here. As voltage increases, the current will reduce. Okay, so this is actually nothing but the negative resistance region. Okay, and let me write it on the negative resistance region. Okay, so this is how the tunnel diode works. So what we can say is nothing but this part we have the tunnel diode. Let me write it down as TD only. Okay, so the tunnel diode works in this particular location. Okay, so that's important. So yeah, I'm not giving you the range of voltage. The range of voltage is something similar to Schottky diode. It doesn't differ much. Okay, so what happens is if this is the case, if the voltage is low, it will conduct well. Okay, so at low voltage, okay, low voltage tunnel diode. Okay, I've written TD, so I'll just write it on this. Conducts good. Okay, or it will have a very good conduction mechanism. Okay, and what happens is if we have lower resistance, the conduction process will be more. Okay, so if the voltage is less, the resistance is less. Okay, because if the voltage is more, the current is more. I think this is also simple, quite obvious. Okay, maybe I can just write it down here. If the voltage is more, okay, the current is less. That is what is negative resistance is all about, right? And if the current is less, it obviously means that it has got more resistance. Resistance more means current less. Okay, so if you have a lower voltage, okay, the resistance will also be less. So lower voltage, resistance less, that means we are going to get more current. Okay, and when will the resistance be less? If the width of the potential barrier should be there, otherwise the tunneling effect doesn't work. Okay, but if the width of the potential barrier is thin enough that the electron can cross from one end to the other end, we can usually call it to be a good tunneling device. Okay, so we can call it to be a good tunneling device. Okay, so basically what happens is we achieve it by heavily doping it. Okay, so okay, NR, negative resistance, is achieved by heavy doping. So I will just leave this question to you. How come heavy doping leads to negative resistance? Okay, just think about the answer. Should not be very complicated. Okay, just think. I'll give you time, and then you can always think, and then you can probably answer me this. So that's important. So negative resistance. So what happens is that this will actually permit the electrons to actually tunnel through the barrier region. So if you have a depletion region, then only we talk about tunneling. If there is no barrier, there is no question of tunneling as such. Okay. So application, maybe we can actually use it in a tank circuit. So in general, whenever we are having electrons playing a role in uh, conduction process, the chances are that because of the resistance, the current will die off. Okay, but then if there is tunneling effect, the chances are that the electrons will actually still be there in play, and we can still have the conduction process going on. Okay, so what happens is something like a tank circuit. So you remember tank circuit is nothing but an LC circuit. Okay, tank circuit. I think we are also going to talk about tank circuit later. Okay, so it is based on oscillation. Okay? It is based on oscillation. Okay, so we have a tank circuit. It will basically oscillate. Oscillate means the charge carrier actually generates, and then again the capacitor starts discharging. Again, it actually powers on the circuit. So it keeps on oscillating and it works out that way. Okay, oscillate but then die out. It's not that it is going to go on forever, because there is conservation of energy, resistance, loss of power, and so on. Okay, so this happens mostly due to internal resistance. Okay, so this is important. So what happens is, if we use a tunnel diode will, let me write down that sentence here, provide a negative resistance. So if we have a device which is actually in which the current actually dies off because of the resistance, if we apply something which is opposite nature, that means we are applying a negative resistance, it will happen that that will actually negate the losses. Okay, so if we provide a negative negative resistance, the losses are overcome. Okay, and the oscillation is maintained, and the oscillation is maintained. So something is ideal and something is practical are two different things altogether. So in general, we expect that they should keep on oscillating forever, but then this oscillation time can be increased by using a tunnel diode. But then there are other effects because of which it's not that keep on going on forever and ever. Okay, because there are certain devices which is, or motion, which we call as perpetual motion. That means once you apply some kind of energy to it, and that energy will be itself sufficient for the system to keep on going forever. Okay, and that's very difficult. Perpetual motion devices are actually not even designed, and even if it is designed, we don't have a perfect perpetual motion. Okay, so it is very important. So what happened was, Esaki in the year 1960s actually studied this phenomena, this process that actually happens. Okay, and based on this, he actually gave this idea of tunnel diodes. Okay, or tunnel devices. So if we just remember this diagram that we had, okay, maybe we can just go to that previous diagram to just do a bit of revision here. Okay, I guess I have it saved. Okay, we did it and it was okay. Yeah, this one, this is the one. Yeah, right. So if you look into this, okay, if you remember, even if you have a Schottky junction, you have a metal and a semiconductor. This is the barrier width. But then this barrier width will exist even between two semiconductors also. Okay, so because their band gap or their Fermi level might not be at the same energy level. If you consider something like germanium, or if you consider something like gallium arsenide, the Fermi levels are different. And once we combine both of them, okay, you're going to have energy band diagram, something like this. Okay, and then if you have this energy band diagram, you know that the electrons are flowing from one end to the other end, just like flow of water. Okay, but that only happens if we actually increase the potential. If we increase the potential, or if let's make it forward bias. If we make it forward bias, this will rise and the electrons will flow. But then this portion is still there, and that is the portion where the tunneling effect takes place. So one of the fundamental question is that if I combine any two semiconductor or any two material, do I expect to see a tunneling effect? The answer is no, because different semiconductors when combined, the width of the barrier, okay, will be different. So if for some semiconductors the width might be very thick, the combination of two semiconductors, okay, the width might be very thick, okay, because you have to apply a very large potential so that some amount of electron can flow from one system to the other, and which actually affects the width of the barrier. So if that happens, the electron might not tunnel at all from one end to the other end. Okay, so it's all probabilistic. So that's why you cannot take any two semiconductors and try to make a tunnel diode. There are certain system, and one of the most important or some of the most important materials that are basically used is, maybe I can just write it down. I think I will already written it, but then there are additional to it. Okay, okay. did I write germanium and okay, so I've written it here. Okay, generally made up of this. Okay, so maybe I can just add some more. Okay, some more examples. So we do have germanium gallium arsenide system. Okay, so it can also be made up of other materials. Okay, so sometimes even they are using this indium gallium arsenide. Okay, so that is also possible. So let me take a tertiary material, another example, and there are other examples also. So even I have not checked all the materials, but then there will be. Okay, and aluminum gallium arsenide. Okay, so these two are also behaving like semiconductors, but they are tertiary compounds. So they are ternary. That means you are having three different elements actually combining to give you a semiconductor. So they do have semiconducting behavior, and if you combine them, the chances are you can also get a tunnel diode from them.